Well, for those already here, welcome. I'm Mike Riddle, and today we're going to be talking about sag and tension theory. This is the second part of this particular topic. We've still got a few minutes before the top of the hour, and then usually I'll give it like a minute or so before we actually get started. But glad you're already here. The early bird catches the worm and all that. Of course, that's not really so appetizing, I guess, unless you're a bird. Well, welcome for those of you that have already joined us today. We've still got about 3 minutes before the top of the hour, and then I usually give it a minute or two for people to roll in. And welcome for everybody who's here. Today we're going to be talking about sag and tension theory. This is the second of two parts on this particular topic. We've still got a minute or so before the top of the hour. Well, for everybody already here, welcome. Still got a few seconds till the top of the hour. And officially, we're at the top of the hour. I will give it another minute because people are still rolling in. But welcome for those of you already here. I'm Mike Riddle. Today, we're going to be talking about sag and tension theory. This is the second of two parts on this particular topic. We're officially at the top of the hour, but I see people are still coming in, so we'll give it maybe another minute, at most two, and then we'll get started. Oh, and I forgot to close the door to my office. I'll be right back and then we'll get started. Okay, I'm back. All right, welcome. I'm Mike Riddle, and today we're going to be talking about sag and tension theory. Alexis, can you confirm that you see my cursor?
I don't see it.
You don't see it. Okay, so you don't see it if I'm there. Do you see the laser pointer?
Yes.
Okay. I'll use it after all. All right, let's get started then. So first up, this is an RCEP compliant presentation. This just means that we've met the standards of their program and we can give continuing education credits for today's presentation. This does not, however, mean that they endorse or approve of any of the content of this. It just means that we've met their presentation criteria. And we'll tell you how to get your continuing education credits at the end of the presentation. So today's purpose and learning objectives. So we're going to talk about what a SAG chart is, what inputs go into generating a SAG chart, what outputs are included in a SAG chart. We're going to talk about the ruling span concept and when it applies and when it doesn't apply. We're going to see how to calculate the actual sag and tension in a particular of a specific span in a ruling span segment. Along the way, we're going to learn about the difference between mechanically coupled and mechanically independent spans and how this affects our sag and tension calculations. And then we're going to learn about how MRDT and MRDT is used for OPGW and MRCL is used for ADSS. They mean the same thing, just different terms. We're going to see how those terms and zero fiber strain margin, how they should be checked as part of the sag and tension generation process. So you've already had the introduction and the learning objectives. Now we're going to hit the presentation. I apologize in advance. I hope I don't go long on this. We'll see. Please save technical questions to the end. We'll open the door, and then I'm willing to stay as long as people got questions. When we can talk as long as you would like. So let's get going. So first up, we all learn from people before us. And on this particular topic, I want to thank Joe Rinaldan. He was the principal standards engineer at Florida Power and Light. He retired from there a long time ago, but he's still active. And in fact, I believe he's working for Avangrid now. And he does consulting as well. And he's especially excellent at anything that's failed. So if you've got a problem with a cable or a fitting or just about anything else that's broken or failed when it shouldn't have, reach out to him. He's a great guy and an excellent resource. So I mentioned already, this is the second part on this particular topic. The first part was last month, and it was cleverly entitled Sag and Tension Theory 101, and this one is 102. In that presentation, we learned four fundamental concepts about sag and tension and cables. And we're going to quickly recap those. Aerial cables expand and contract with changes in temperature. And elongation is the term that we're going to use for these changes. Metallic cables change a lot relatively. Non-metallic cables change a little relatively. Cables with mixed construction are probably somewhere in between. And elongation changes that are caused by temperature changes alone are elastic. So you heat a cable, it expands. You remove the heat, it contracts and goes back to where it was before. So it's reversible within the normal operating temperature range of aerial cables. Aerial cables also undergo creep, which is permanent. We use the term plastic, but it's irreversible. So in that case, the cable has been stretched. This comes from its own weight. And so the cable elongates a little bit, but it doesn't go back. It never goes back. And it's one of the reasons that there's a difference between the initial sag and tension for a cable, which is to say what it is at installation, and the final sag and tension of a cable, which is taken as 10 years later. The other cause is plastic elongation due to wind or ice loading. And then just as a reminder, if there were no plastic elongation in a cable over time, then there would be no difference between the initial and final sags and tensions of a cable. So it's the fact that there is plastic elongation that makes us have to kind of look at this and think about it. The third thing that we learned was that the effects of 1 and 2 taken together with our design conditions, or what we're going to call loading conditions, plus any limits that we place on the sag or tension, will determine the final sag and tension values for a cable. And the values that result from this process are our sag chart that we're going to see. So we're going to look at the inputs, the calculation process, and then the sag charts, the data that you get out from this process. In the United States, and I have to apologize to the rest of the world or any other international customers that are attending today. This particular presentation is very American oriented, not only because I'm American, but this is the environment in which I've done sag and tension calculations over the course of my career. The truth is I have really little to no idea how it's done outside of the United States. So I apologize. There are fundamental concepts here that would apply outside the United States. But again, this is a very American-oriented presentation. I'm sorry for that. So the two programs used in the United States are Southwire SAG-10. This software goes all the way back to Alcoa software on mainframe computers. Remember those? In the late 1950s. It was a computerized implementation of a graphical method that was used before to produce sag chart data using what's called a light table. Southwire maintains today's version, and you can find information about it on their website here. The other program that is commonly used is Powerline Systems PLS CAD. In addition to generating sag and tension data, it does a lot of other things too. It helps you spot structures and check clearances and other things. And you can find their website here and information about that program on it. Now, the two programs look completely different. But it actually turns out that the sag and tension calculations are done using the same basic methodology. The reason I put this little qualifier in there is each has its own little bells and whistles kind of add-on things. And I don't know the specific algorithms that are, what's actually going on inside each. But the basic methodology that we'll talk about today is used by both programs. So, how do I know that's true? And I've already explained the basic caveat, and then assuming it is true, what is that shared methodology? So let's delve into that question. So how do we know that they're using the same methodology? Well, because both are using at least two sets of coefficients that describe a fourth order polynomial that models the initial stress strain curve for a cable, and a fourth order polynomial that models the final stress strain curve for a cable. How do we know that? Well, in SAG-10, if you look, you'll see a reference when you select your conductor, you'll see a reference to a chart. Here they've entered Drake, which is a common ACSR, and its chart number is 1-537. If you go find that chart, this is what it looks like. It appears kind of simple, just bunch of numbers in a text file. But what does all this mean? Well, if you look at their input screen, it begins to tell you what it means. There you'll see polynomial coefficients, all strains in percent, A1, excuse me, A0, A1, A2, A3, A4, and then there are values there. You've got an initial, and then what's on this screen is referred to as a creep, or you can think of it as a final. Additional data is the temperature that the stress strain test that was used to generate these coefficients, what temperature that test was performed at. And you also find some additional information there, the final modulus of elasticity over here, and the thermal coefficient of expansion is here. Later, we'll talk about why there's outer strands and why there are core strands and what that means. But you see this repeated. So another set of coefficients and a final modulus of elasticity and a coefficient of thermal expansion. So that's Southwire SAG-10 program. So now PLS CAD looks different in part because they use what's called a wire file to set up your model that you're going to use to generate the data. And a wire file looks like this. It too is a text file, but then what you see is buried in it is this chart reference, and then a bunch of coefficients. So again, concept is the same, but the presentation and the human user interface of the two programs is quite different. But underlying everything, they're doing things essentially the same way. So here, I was just showing that you see exactly the same thing. Oops. Okay, now, I said there's two sets of polynomial coefficients, but when we looked at the data for 1-537, there appeared to be 4. And in contrast, in the PLS CAD wire file, it referenced a chart 1-1450, and it had a bunch of zeros in it. So again, it had zeros. It had two sets of data. You see it better up here, perhaps. Why? Well, 1-537 is a chart that was originally done for an ACSR. And a long time ago, we're talking late 50s and in the 60s, it was a common practice for coefficients for ACSR to be separated into those for the aluminum outer layers and those for the steel core. Why was this done? Well, it allowed you to scale an ACSR conductor design up or down, maybe to better meet a specific ampacity requirement without having to go completely redo the stress, strain, and creep test. And that scaling was done by keeping the percent steel relative to the percent aluminum constant. So the thinking is I can make it bigger or I can make it smaller, but mechanically it's going to behave the same way if the steel and the aluminum are essentially in the same ratio. And then this concept has been extended to OPGW. OPGW was not around in the 50s or the 60s. By matching an OPGW design to a particular chart number using the percent steel content, and then using an existing chart for essentially a new OPGW design. So, okay, so that explains why one chart has what looks like 4 lines of coefficients, not just really 2. Why does this other chart have a bunch of zeros? Well, because if you didn't break or separate out aluminum from steel, then you did things as a composite cable. Like you could do that for an OPGW, test it as a single integrated cable or a composite cable was the terminology that was used. There, in that case, you only needed the one set or one pair, an initial and a final set of coefficients. The other reason that you might have all zeros is a homogeneous cable, a cable that only has one material in it. So a double AC conductor or triple AC conductors are that way. Aluminum-clad steel cables, like your 7 number 8s or whatever, your 3/8-inch galvanized cables, things like that. Homogeneous cables don't need two sets of coefficients for them. And I kind of pointed this out already. If you looked at the Southwire's SAG-10 program input, you actually see that they explain this set of data is for the outer strands, and this set of data is for the core strands, if different from the outer strands. So you don't need this if it's a homogeneous cable or you're treating the cable as a composite. So you have these charts. Both SAG-10 and PLS-CAD have a library of charts that are available. In SAG-10, if you know the chart number, you can just enter the chart number for a cable. And for many standard conductors like your ACSR cables, a chart number will automatically come up for those cables. In PLS-CAD, they have a library of wire files by cable type and manufacturer on their website. So each of their wire files has the sag coefficients included in it. So now we've learned about sag coefficients. What other inputs are needed to model a cable? Well, here's some basic information that both programs use. The cross-sectional area in square inches or millimeters squared, and sometimes the aluminum and steel are separated. You also need to know the outer diameter. You have to have a unit weight, and you have to have a rated breaking strength. This is all basic data that are on typical cable data sheets, or you can find published data for many of the standard conductors that are in use today. Let's see how it's done in SAG-10. I showed you this before. The conductor selection, here it is for Drake. You can see that the basic data is there. I apologize, the picture is a little bit fuzzy, but kind of trust me, it's there. And you'll notice that they separate the steel and aluminum. But remember, if you know the aluminum area and you know the total area, then you're able to calculate the information that you need for the steel. And then here's how it looks in PLS-CAD. In a wire file, you still have basic cable data. So here's the cross-sectional area, and notice that they don't separate it in PLS-CAD. Here's the cable diameter, here's the weight, and then here's the rated breaking strength. Next up, you need to consider what loads you're going to have on the cable, and there are 4 that are possible. First up, wind. So as we talked about in Theory 101, wind blowing across a cable will impart a load on it. And if it's strong enough, it'll elongate the cable. Ice that accumulates on a cable will add weight, and the weight will elongate the cable. There's also an NESC K factor. This is specific to the US, and we'll talk about it more in a minute. It's an added load that varies by loading district. And then you can have other loads. Basically, anything that adds weight potentially can elongate the cable. Typically, the most important are wind and ice. I mean, you see them all of the time. Other loads can be a factor, and then NESC K factor, well, that's just a code requirement, so you have to use it. First up, let's talk about wind. Wind blowing across a cable, as we already said, it can potentially elongate it. It's expressed as a pressure, pounds per square foot, which equates to newtons per square meter. You can convert the wind speed, because most of us think about the wind in terms of its speed, not its pressure. There's a simple formula for that. And again, I have to apologize to international listeners that I did not convert all of these equations. I kind of leave it on your own to do that as a separate exercise. So anyway, it's this formula. You can grind the math yourself. The total wind load is the pressure times the diameter of the conductor plus 2 times the thickness of any ice. So notice that the presence of ice effectively increases the total wind load. You've made the conductor or the cable bigger, therefore it picks up more energy from the wind, which is what's elongating the cable. This formula again is in customary units. So diameter of the cable plus 2 times the thickness, and then you're dividing by 12 to convert it to feet so that you get a final wind load that's expressed in pounds per foot. Next up, ice. Ice adds weight. Again, it's going to be pounds per foot is where you're going to end up. Ice loading will vary upon the density. So glazed ice versus rime ice versus hoarfrost versus wet snow and whatnot, they will have different densities, which means they add different loads. What's most common is to consider what's called glazed ice, which has an assumed density 57 pounds per cubic foot. In any case, the total ice loading, assuming this glazed ice, there's a formula for that. And again, you see the diameter of the cable and the thickness of the ice as important variables. If you have both, you need to use a different formula to add them correctly. You can't just add the wind load and the ice load together. Instead, you need to use this formula. It's square root weight, cables bare weight plus the ice, weight of the ice squared plus the wind loading squared. Straightforward. Now, so talked about wind load and we talked about ice load. Now this NESC K factor. It's often called a safety factor, and strictly speaking, that's not really true. It too is a load, so pounds per foot. It varies by the district, and I'll show you that in a minute, whether it's a heavy, medium, or light loading district. What is it? I was told years ago by a graybeard conductor engineer that it was a correction factor that resulted when converting the graphical method that I mentioned previously that used to be used in the 50s and 60s. When they went from doing that graphical method to doing a computer method. The reason he said was that the graphical method was actually based on parabolas. Remember, we talked about that in Theory 101. It's a simplification of the catenary, which is a lot harder to calculate. So in the old days, to make it easier on themselves, they were using parabolas to calculate sags and tensions as well. When they decided to go to computers, it made sense to just go ahead and use the actual catenary formulas because the computers could handle that. But then you had to correct what had been done before so that old SAG information could match new SAG information and vice versa. That explanation sounds good, but I can't verify if it's really true or not. That gentleman is long gone. I tried researching it. I could find nothing that confirms that this is really true. It seems people started calling it a safety factor because that's just a human means of trying to categorize it. But as I say, I really can't confirm, what is its basis. So I have to say NESA K factors are what they are. Just kind of live with them. Last up, any other loads. Anything that could add significant weight should be factored into the calculation. Things like marker balls in particular, PLP airflow spoilers, which help prevent galloping. Other cables or cables that the cable will support. So a cable that's being used as a messenger cable, you need to calculate its sag and tension data different than just a standalone cable. A variation of that, or maybe a specific implementation of that, is the Hendrix spacer system will add significant weight to a cable and should be factored in. So we're not going to look at these in detail today. You just need to know that added loads equals added sag and therefore increased tension. Please know that both SAG10 and PLS-CAD do give you an option for including additional loads when you're doing your calculation. So look for that feature in both programs. So next up, standardized loading criteria. So the United States has several sets of standardized loading criteria. The most widely used, we've already mentioned, NESC. There's also RUS, which is kind of a variation of the NESC. There's California GO 96. Hawaii uses something like this too, as I recall. And there are some others that are specific to states or regions of the country. And other countries and provinces around the world, I'm sure, have their own standardized sets of criteria. A standardized loading criteria gives you a starting point for determining what wind and ice loading to use when you're generating your data for a specific geographical location. So here in the United States, as an example, the NESC sets. So you've got heavy, medium, and light. You can see how they are on the map. And you can go on the internet to refine this. So you can put in your city and find out which specific loading district that you're in. Note that these have ice and wind, and that they're applied at a specific temperature. And that's really important because if you'll remember from before, we said metallic cables change elongation significantly in response to changes in temperature. So that's why you have to know a temperature. And then here are those K factors that we just talked about. You can see you add 0.3 pounds per foot in the heavy districts, and then by the time you're in the light district, you're only adding 0.05 pounds per feet. And then mention too that while temperature is significant for metallic cables, it's actually ignored for ADSS because the difference in how ADSS responds to temperature changes, which really amounts to it doesn't. So that's why it's neglected. So in addition to having how much wind and ice and whatever else you're going to add on a cable, you also apply specific tension limits. And so for the NESC, you talk about initial tension at the full load must be less than 60% of the rated breaking strength of the cable at that temperature. And you can see the other ones here. Initial tension at no load, so without the wind or ice, limited to 35% at 60 degrees Fahrenheit. Final tension with no load, 25% rated breaking strength, again at 60 degrees Fahrenheit. The NESC also has these extreme wind conditions. You see the wind load that corresponds to 90 miles an hour, and you limit the initial tension to 80% of the rated breaking strength of the cable at 60 degrees Fahrenheit. Concurrent ice and wind, you can see the values that are here. And I want you to realize that there's a pattern to it. So there's a structure to it. All of these have 4 elements to it. You have a specific load. You apply it at a particular tension to a particular tension limit, applied at a specific temperature to a specific tension limit that's expressed in the rated breaking strength of the cable. And then you have to have an indication whether that limit applies at the initial condition, meaning immediately after installation, or if it's at a final condition, which is taken as being after 10 years. We talked about this before, why that is. Now, if you come up with your own criteria, you would also have to have these 4 elements. Likewise, if your state or your country or province or whatever, if you have some standardized criteria, I am sure that they have these same 4 elements to them. Now, to give you an example here, if you were living in Hawaii and you wanted to consider 120-mile-an-hour wind, you can calculate the wind load, gave the formula before, but then you still have to decide what temperature it's going to apply at. I said maybe 70 F, and what the tension limit would be. I picked 80 percent rated breaking strength, and whether that limit is at initial or final condition. So you still have to have these 4 elements. So why are those particular tension limits used in the NESC code? And the answer, basically, it's because they work. You remember the story of Goldilocks and the 3 bears. The porridge was too cold, or it was too hot, or it was just right. And these limits work like that. If the final tension at 60 degrees F was below about 10% rated breaking strength, then the sag would be quite large, and then structures must be taller, and then that means they're going to cost more. Tension too low, you could characterize it as. If the final tension at 60 degrees F was above 25% rated breaking strength, then the cable is going to be highly susceptible to alien vibration damage. So the sag would go down, but the cable would be very susceptible to alien vibration damage. So you could say the tension is too high. So it turns out that the limit of 60% rated breaking strength and the other limits there are very practical. They work well. In particular, the 60% gave you a margin for error for more severe weather conditions to happen, right? Your design condition is just an assumption, half inch of ice and however much wind it was. Mother Nature could give you an inch of ice, or instead of 40-mile-an-hour wind, it could give you a 50-mile-an-hour wind. So using this limit gave you a margin for error. And then it also turns out that the reason you see the extreme ice and concurrent ice and wind loadings limited to 80% is because it turns out that prolonged exposure on metallic cables to a tension greater than 80% rated breaking strength can cause the cables to begin to have effectively deteriorate structurally. Changes in the grain structure come about, and nothing good happens, and so bad things can happen. So they work well. And I'm sure that elsewhere in the world, they have similar limits because they work well. So let's recap this process, because I know I presented a lot there. You need to determine your base loading criteria, NESC or whatever it is for your state, province, or country. If you're going to consider extreme ice or high wind conditions or a combination of the two, add those in. And then if you have any unique criteria to your specific project, or perhaps your utility tension limit, you don't want to go above this, or you don't want the sag to be more than that, well, then add those in as well. So each program has its own way of putting these inputs. So here's the screen for SAG 10. You can see you can pick light, medium, heavy loading. You'll see they have the RUS ones too. They even have the California ones over here. And then this is how it looks in PLS CAD. Both programs have the commonly used standardized loading criteria, but you have the ability to add and customize loading criteria. And then there's a second screen, or like in case of PLS CAD, it's the same screen technically, but a different location where you add in or customize tension limits. So next up, span data. So we've got our basic cable data now. We've talked about loading criteria, and we've covered tension limits as well. So there's one more input that we need, and that's the span data. So it's going to turn out that how we look at the span data is going to depend upon how the cable is installed and how it will operate after installation. If a cable was pulled in using stringing blocks, which there's probably a dozen different names for them, pulleys, travelers, rollers, whatever. But if a cable is pulled in using stringing blocks, it's usually pulled in, like always pulled in really, using what's called the controlled tension stringing. So you're controlling the tension and the cable is going over these blocks. Because the cable is free to roll across the stringing blocks, the horizontal tension is going to equalize at each structure across the line segment from dead end to dead end. Or now, technically, when you're pulling in, the dead ends aren't installed, so you could still think it as first structure and last structure, or beginning and end, but the concept still applies. All the structures, the horizontal tension is going to equalize at. That's the main point here. The horizontal tension will equalize. Okay, that then begs the question, at what tension will it equalize? Well, turns out that it's going to equalize at a value that is closer to that of the longer spans, but it's going to be kind of a weighted average is the way to think about it. And in fact, there's going to turn out that there's a weighted average that you can calculate that will characterize exactly how the cable is going to behave and give you, lead you to the prediction at what the tension is going to equalize at. And we call that weighted average span the ruling span. So you've got a whole bunch of spans and you've got a ruling span, one span to rule them all. And the calculation for that is it's the square root of the sum of the spans cubed divided by the sum of the spans. And here's the detailed formula for that. And this comes from an equation developed by a man named E.S. Thayer way back in the 1920s. So here's what that looks like. Here's 10 spans. Here are the spans. Cube the spans. Da, da, da. Don't cube the spans. Add them up. And this ruling span is the square root of this divided by this. And just for reference, I wanted to show you the average span here. If you calculate the average, you get 660 feet. But if you use the ruling span calculation, you get 716 feet. So, a couple more tidbits before we move on. Because the tension equalizes in a ruling span segment, we say that that span is mechanically coupled. So what goes on in one span affects another span. And I said this was during installation. Well, what happens after you've clipped in a cable? Well, if the attachment points can move in responses to changes in horizontal tension, things will continue to equalize. Okay, that then begs the question, how does that happen? Well, the answer is insulator swings, like, or insulator strings will swing. So here's the insulator string. Changes in tension on one side or the other are going to cause this to move. And it only takes just a little bit of movement to equalize the tension on this side versus this side. The other possibility, and you see this particularly with OPGW, is that the hardware, there's not an insulator string, but the hardware allows the tension to equalize because it can move a little bit. So you see this clamp here is connected to the structure via a Y clevis. That clevis can swing a little bit to either side and thereby equalize the tension on one side of the structure versus the other. So this begs the question, if there are mechanically coupled spans, are there instances where that is not the case? And the answer is yes. A single span, so a span that's dead-ended on both sides. Of course, you know, in this case, the ruling span equals the span. So technically, you could still say it's actually still covered by the ruling span concept. Of more interest is mechanically independent spans, where each span acts independently of all the others. How does that happen? Well, with conductor, it would be conductor supported on rigid post or pin insulators. Even then, though, the installation would be governed by the ruling span concepts. You don't see this condition much on transmission lines, but it's very, very true with distribution lines. And you also see this condition with ADSS. So we'll see this with the next slide. So with ADSS, it's often installed on distribution circuits. That's what this illustration shows. So this illustration, the distribution line is also mechanically independent spans because the cable is tied at each of these pin insulators. But the point I was really trying to make was about the ADSS. Because of this type of support, they do not move. They're rigid, fixed to the pole. So the tension cannot equalize once the cable is in operation. So bottom line, what span information am I going to enter into the program? Well, if you know the spans are mechanically coupled, well, you'd enter the ruling span or ruling spans. If it's a really long line, you've probably broken it up into different segments. If it's mechanically independent spans, well, then you got to enter each individual spans. Now, if somebody asks me the question, well, what if we're stringing through blocks, which would lead to a mechanically coupled situation right after the cable is finished stringing, but then we're going to clip such that the cable can't move, which would be mechanically independent. Well, the way I would do it is I would generate the data using the ruling span concept, because that's how the cable is going to behave during stringing and immediately before you clip it. But then what you should do is go and check load imbalances in places where there's a long span adjacent to a short one. So once the cable is clipped, wind and ice load on the long span could lead to a much higher tension on that span versus a short span next to it. Yeah. Whatever is the attachment point, it's going to have to absorb all of that. So you should check that. What's a long span versus relative to a short one? I don't know. I would look at any case where there's more than 50% difference relative to the short span. Rough guideline. Both SAG-10 and PLS-CAD have a screen that allows you to enter the span information. And PLS-CAD, you can enter a series of spans and it will calculate the ruling span for you. So each program has its own way of adding the, I've already covered this. How did I get back here? You enter the loading criteria, NESC, you can customize your loading criteria and you have a screen. I covered that already. Anyway, so now we have all the data that we need. We got our sag coefficients, we got our basic cable data, we got our loading criteria, we got our tension limits, and we even have the span data now too. So now we can hit in SAG-10, calculate sag and tension button, or in PLS-CAD, there's a sag tension button. So let's get our data. Let's look at what the programs are doing to generate that data first, and then let's look at the output that we're going to get. So the programs, what they're doing is they're calculating the sags and tension for each combination of loading condition and tension limit that you enter. So if you've entered, say, 3 or 4, it's going to calculate it for each one. It's going to figure out which one of those 3 or 4 is the design condition, which is to say which one controls the tension. And then once it's found that, it's going to go back and recalculate the sag's intention for the other loading conditions based upon that design conditions. So let's look at that. Calculate sag intentions for each combination of loading conditions and tension limits. So remember, we had our sag coefficients. They model a curve that would look like this. And for fun, you can go find a graphing calculator and you can generate the curve yourself. So what the program is doing is taking loads, converting it to stress. So you find where your stress is at, you go to the curve, and now you know how much elongation you have. Once you know how much elongation you have, it's pretty straightforward to calculate the amount of sag that you have. And then, of course, the stress converts to a certain amount of tension or to a specific amount of tension. So you have to do that for each set of loading conditions and tension limits that you have. Now, I just want to comment that it's easy for the initial condition. It's conceptually very straightforward. I just basically showed it to you. It's the final condition that's less straightforward. You have to make a couple of assumptions, and both of these assumptions could be challenged. First assumption is that creep finishes in 10 years. Well, it's actually one of these things where it approaches an asymptote and in theory continues forever. The second thing that you're assuming is you have to assume a certain amount of plastic elongation due to the highest load that you designed this cable for. Remember, you had to have the reason that you have a difference between initial conditions and final conditions is that the cable is elongated. And they're the two sources of elongation. The creep that was always going to occur anyway, just because of the cable being under its own weight, and then any additional loading that caused the cable to stretch even more. So your wind and ice loading, and plus the other things that we talked about. So which is the design condition? It's easier for me to explain how this is done using an example. So remember I talked about an engineer in Hawaii, and that person wanted to use or wanted to consider a 120 mile an hour wind. So let's say that they started with the NESC light conditions, plus they added that wind condition, and they decided they were going to apply it initial with a limit of 80% rated braking strength at 70 degrees Fahrenheit. And let's say they also added a final condition that with no loading on the cable's tension should not exceed 20% rated braking strength at 60 degrees Fahrenheit final. This is a good limit to use for keeping Aeolian vibration manageable. Doesn't drive it to zero, but it keeps it manageable. If you go above this, you really should be doubling up dampers. All of the damper manufacturers will tell you that. And so now it's included in both programs, by the way. So let's add these. So now we have 5 cases to check. We have 3 from the NESC at full load less than 60%, at no load initial less than 35, at no load final less than 25. This is effectively going to be canceled by this one, but we still have to check it anyway. And then we have this high wind one that we added. So conceptually, what the program is going to do it's going to start with probably what it thinks is the highest, which is probably the standard one, find a solution for it. Once it finds that, it's going to then calculate the second one. And does that solution lead to a condition where this condition is also met? If yes, it's going to move down and keep going. I think that makes sense. What if there's a problem though? So let's say this one was met, or it started with this one. This one led to conditions where this was met and where this was met, but then this failed. Well, this then you start over. Now you find a solution for this and then apply it to all of the others. So conceptually, this is how the process works. Now, the algorithms, I don't know their details, so I'm sure they have something that differs in its particulars versus what I'm doing, and I don't know how they pick the starting point. But the concept, I think you'll understand. And in it, what you get out of this is the condition that controls, meaning the one condition that leads to solutions that work for all of the others. That condition is referred to as the design condition. And that will be noted on the sag and tension output that you get. And then once you have a solution, the program is going to use the coefficient of thermal expansion to calculate sag and tension for any other temperatures that you indicated you wanted data for. Because remember, metal cables will elongate just in response to temperature changes. So that's how that works. So a couple of closing thoughts on this particular point. Is it possible to have so many conditions or conflicting conditions such that there is not a solution? Yes, absolutely. And you'll get an error message to that effect, and you've got to go back and change something. Secondly, is it possible that two or more conditions reach the same solution? That too is the answer is yes. And you'll get an annotation that there is a common point, a common design point. So we had all of our inputs. We ran the program. We got our output. Here's what that output is going to look like. This is from SAG-10 for a cable. You see its chart number here. You see some basic information about it up here. You see the ruling span. And here's your output. You see where you had the NESC heavy condition. This particular utility had an extra ice and wind condition that they looked at, 1.5 inches of ice with a 2-pound wind at 30 degrees Fahrenheit. Other temperatures they wanted to see the data for. And you see here, this was the condition that controlled. So they limited tension to 3,500 pounds. And that design condition is indicated with an asterisk. And you see a horizontal sag and vertical sag initial, and then you can find the final. After 10 years, the tension drops and the sag increases, no surprise. PLS-CAD's output data will look a little bit different, but it's the same stuff. And even within SAG-10, you can customize the output reports. Here, for whatever reason, I separated horizontal and sag from vertical sag. You can get it as just the resultant sag. You can also get it to display a column showing the percent RBS. Often you want to know that. For whatever reason, when I generated this, I didn't do that. So that output was for a ruling span, or we can assume that it was. What if I had a particular span within that segment that I wanted to look at? Well, here's the formula for calculating what the sag is in a particular a particular span within the ruling span segment. It's the span you want to know about. You calculated sag using the ruling sag of the ruling span times the sag of the actual span divided by the sag of the ruling span squared, and you'll get sag where you need to know it. And you can do the same for horizontal tension. So before we move on, we need to look at two manual checks that neither SAG-10 nor PLS-CAD do, and these are specific to OPGW and ADSS. You need to ensure that under everyday conditions, 60 degrees Fahrenheit, no load, initial and final condition, that the tension on the cable is less than the cable's zero fiber strain margin. Fiber strain kills cables, especially if it's above 0.2%. And this zero fiber strain margin is the point where fiber strain begins. It should be on the cable manufacturer's data sheet, but if not, then you need to ask for it. You also need to check the MRDT, maximum rated design tension, or the MRCL, maximum rated cable load. They mean the same thing. For whatever reason within the IEEE, they picked different terms for the two types of cables, but they really mean the same thing. It's the maximum tension that the cable should experience for design purposes. If you exceed that, you are asking for optical problems and avoided warranty as well. Ideally, strain should be always zero, but the reality is that some cables will have strain at these points. If that is the case, it needs to be less than 0.2%. Unfortunately, a lot of cable vendors, most in fact, don't show what the strain is at MRDT or MRCL, so you have to ask. They may grumble, but if you ask and insist upon it, they'll give you the information. So in the example that we used, you could check that if the cable had an MRDT 11,309 pounds, 80%, which is pretty common for a stranded stainless steel tube design, you can see you don't have a problem. So working with the output, you've generated the sag and tension data, but for the installation crews, they need to know what the sag should be, or the tension should be, in a particular span at a specific cable temperature. And in order to provide them this information, both SAG10 and PLS CAD generate what are called stringing charts or stringing tables, same thing from a practical standpoint, basically by clicking a button. Here's the button for to generate a stringing chart in SAG10. You fill in some basic information, and then it spits out something that looks like this. And this one I picked in metric units just because it's a nice, clean, neat looking table. So you can see the spans here and temperatures up here, cable temperature, not air temperature, cable temperature. Now, if you'll see 0, 10, 20, 30. Let's say the temperature was 25, and let's say the actual span you were looking at was 110 meters. Well, you can interpolate both points easy. So we've learned about what a sag chart is. We've learned what inputs go into it. We've looked at the outputs. We've talked about the ruling span concept, when it applies, when it doesn't apply. We've looked at how to calculate the actual sag or tension in a particular span within a ruling span segment. We've talked about the difference between spans that are mechanically coupled and ones that are mechanically independent. And we've even looked at how to apply MRDT or MRCL and zero fiber strain margin when you're doing this. For more information on this topic, you should get a copy of the Southwire Overhead Conductor Manual. They deal with it in extreme depth, thoroughly covered there. And you can get a copy at their website. Now, we're done. And you're free to go, and you can take the test and get your continuing education credits. There is a topic that I want to discuss. We're actually also officially out of time too. Takes me probably about 5 or 10 minutes to discuss this last thing, but it's potentially highly disturbing. So I also want to make sure that Joe Biden, oh my gosh, Joe Rinaldi should not get any of the blame for the 5 or 6 slides that are about to cover. So warning, you can drop off now, really, no problem. Last chance. You can go get a cup of coffee and come back for the questions and answers in about 10 minutes. That's also an option for you. All right, let's hit it fast. So most sag charts are wrong. I'm sorry, that's just really true. Even when I alluded to this in the sag and tension theory 101, I said when talking about sag error in the field, I made a comment that there is error in stress strain curves. There's several reasons for this, which we're not going to discuss. This is now when we're going to talk about that. Really, there are two big ones. One, charts are the charts that are used today are based on data from the 50s and the 60s. And then the second thing is those charts don't cover the full range of elongation that cables could experience in the field as used today. I should have added here, as used today. So let's look at these points. Error number one, the charts came from the 50s and the 60s, and there wasn't even OPGW around yet. Okay, why is that significant? Well, because production and quality control processes for both steel and aluminum have changed and really improved over the intervening decades. So the wires are different than they were back in the 50s and the 60s. Plus, cable stranding has changed, especially for conductor. You use, back then they used planetary stranders. Today, these fancy bow or rigid stranders and even tubular stranders are out there. Much higher production speeds. It's actually arguably not as good quality stranding as planetary stranding, in part because more stress on the wires. Today, planetaries are used pretty much just for OPGW. But even today's planetary stranders are better than the ones back in the 50s and 60s. They have better lay length and braking control. So net result, today's cables are different. So really, what's being used today is different than what was tested in the 50s and the 60s. Now, is different better or worse or no net change when it comes to sag and tension? Hold that thought for a minute. So, second source of error is that most charts are not covering the full range of elongation. That's because the testing back then was generally done to a strain of about 0.5%. Roughly 50% rated braking strength, plus or minus 10, might even be more. But today, not only are we expecting cables to perform up to at least 60% rated braking strength, but with extreme ice and concurrent ice and high wind loads and whatnot, we really want the cables to do up to 80%. So we're taking them beyond where the test data actually covers. Both programs deal with this by extrapolating the curves, but extrapolation implies errors. And of course, that begs the question, how much of an error? So what's even more confounding is that you can't look at a chart and know at what limit the test was performed at. You can only make an educated guess. So when I showed you this curve, you probably didn't notice that I ran it only up to 0.7%. Why did I do that? Well, because it looked about right. Truth is, I didn't know. I just guessed. 0.5? Okay, it could be. I looked at that and said, it looks a little bit too straight. I did 1% just in case. Absolutely not. Look at the strange shape you get at the end. So I figured, it probably did it to about 0.7. So that's what I generated the curve for it. Again, the main takeaway is I don't know what the test was because there's no information in the file to tell you that. They gave you the test temperature. That was nice of them. Why they didn't say we did it up to 0.5%? I don't know. Beats me. So, given the shocking news, why are transmission lines not falling down all over the country every day? Well, my best guess about this question of the difference is that difference is better on balance. So the improvements in the production and quality control processes likely means that on balance, it's taking more stress to produce a given strain. Plus, there's more consistency in today's wire, which means you're less likely to have a wire break prematurely. And so if this is true, then today's cable likely sag less than the calculations would indicate if you're going by tension during sagging. Or the flip side. If you if you sag a cable and you go by the sag, 3 feet of sag is it's supposed to be or whatever. If you put it at 3 feet, the actual tension is probably lower than the calculations are suggesting, would have you believe. So these errors can be considered favorable. If the actual sag is less than what you think it is, or the actual tension is less than what you think it is, that's good, right? It means your clearances are maintained, and it means your structure probably, like in my hypothetical Hawaii example, you designed it for 120. Well, effectively, because of the error, maybe it's good for 140 or even more. I don't know. My comments here are consistent with my observations about OPGW sagging in the field. I did one project in particular where the construction line supervisor was terribly distraught about the fact that they had used a dynamometer to bring the cable to its initial tension. But he said, "Oh, that's sag. That's too low of sag. Something must be wrong." And I assured him, no, don't worry about it. It's actually a not bad thing. So in theory, couldn't you fix this by doing more testing? Let's update all of our tests. In my opinion, I don't think so, because you can't just go do one stress strain test and say that now I've confirmed the coefficients. You have to do a series of them because there's still some variation between a cable made today and a cable made next week. And also there's the fact that really to get creep test right, you have to do 3. So this is a lot of testing that you would have to do to correct for this error. And that's likely to prove uneconomical and take a heck of a lot of time. So it's probably not practical. And it's especially not practical as an OPGW manufacturer, because in your Southwire overhead conductor manual that I mentioned earlier, if you look it up, you're going to find that there are 54 standard designs, roughly. But everybody who makes OPGW has literally hundreds of designs. And for one reason or another, some are not purchased. So if you did testing, when would you test? When you proposed it? Well, but who's going to pay for that? And what if it's not bought? If you do it later, well, but I had to continue my production processes and engineering had to continue. So you again end up in a situation where it's just not practical. And that's why the matching that I've talked about earlier has been used. So, conclusion, let's pretend we never had this part of the presentation. The current practice is clearly not perfect, but it does work good enough. My best guess is the error is on the order of 10% and in a favorable direction, as I already mentioned. Plus, as we mentioned before, best guess is that the field error in doing the sagging itself is probably at least as much. So as an old song put it, don't worry, be happy, but at least now you know. So thanks. I appreciate those of you that hung around. And now we'll go on to questions. So hit them in the chat, or Alexis can unmute your microphone. Let me look at the chat. Oh yeah, I forgot to tell you. First question, is there a link for the exam? So what's going to happen? Thanks for attending, by the way. You're going to get a follow-up email from us. The follow-up email is going to include a link for the presentation, the video and the actual slides, and a link that you click and you go to a quiz. You pass the quiz with 70% or higher, and you get your credits. And then the third component is a link for a survey. Give us feedback. Okay, so let's see. You received follow-up email. I'll have to jump to another call. Thank you. Can I hear you? Oops, sorry about that. I need to drop. Thanks so much. Thanks. Yeah, okay. I appreciate all. Thanks. Any questions?
Yes.
Yeah.
Not really a question, Mike.
Hey, it's
Can you hear
Joe.
me?
Yeah.
I just want to I just want to say that I appreciate very much that last section that you presented, because most folks, I think, are not aware of all of these historical minutia and details about, how does that translate into, let's call it precision or accuracy of sagging and tension. And these are the actual explanations for why we in project engineering use buffers in the sag and tension calculations when we're designing a line, because not only are all of the things you mentioned part of the uncertainty of what the exact sag or tension is, and that's kind of a misleading term, because I've come to believe there are no exact sag and tension calculations, and the real key is that there's more error in the installation process than there is in the calculations.
Yeah.
So I just wanted to say that all of that is the basis for why most companies use some sort of a buffer in their clearance requirements for designing lines. So thank you.
You're welcome. I felt I should include it in there because it seemed, what I'm observing is something that seems like the next generation of engineers coming up, that when you run SAG-10 or PLS-CAD, and it tells you the tension's going to be 4,123 pounds and the sag is going to be 11.2 inches, that they think it's going to be, you can go out in the field and it's going to be exactly 4,123 pounds, or, maybe plus or minus a pound. And you're going to measure exactly 11.2 inches, And I just felt that they had to have some understanding that the underlying reality is a little bit different.
Right. One of the things
Jim.
one of the things I'd like to pass along is the story that I got from one of those graybeards way back in the 70s, and was about the stress strain curves, was that the Aluminum Association basically took samples of stress strain curves from the various manufacturers and averaged them to get the stress strain curves that they published, and were subsequently used in SAG-10 and PLS-CAD, and there was no indication. There's really no indication about what the statistics are on those curves. So if they took a point and they averaged 5 different manufacturers, there's no record of what were the outliers. What was the standard deviation on that? Apparently none of that was, if it was ever decided or measured or calculated, it was never published. So there's always been a variation in the older curves themselves.
Yeah, and to build on that point, none of those companies are back in the 50s and 60s that generated the data. None of them are in business anymore.
Mm-hmm. Right. Alcoa, Noranda,
Alcoa, Reynolds, Kaiser.
Yeah, Noranda.
I mean, Alcoa's around, but they don't do conductor anymore.
Right. They don't. Nobody in North America except Southwire, I think, manufactures conductor anymore. Maybe Prysmian. I think they manufacture. I don't know if they manufacture in the U.S., but I know they manufacture in Canada.
Yeah. Well, they acquired General Cable, which
right,
which manufactures conductor, but I don't know. I don't know how much General Cable really participated back in the 50s and 60s with the Aluminum Association and aggregating all that data.
Yeah, I don't know either. I don't have any information on that.
Thanks. I see somebody has their hands up. Please.
Aziz,
Yes, I have one question. You mentioned in presentation horizontal sag and vertical sag. So what's the difference between these two?
Oh, yeah, horizontal sag and vertical sag.
Yes,
So if you only have ice load, you only have a vertical sag. But when the wind blows, it blows across the conductor, and it's going to cause the conductor to swing. And so then the sag really has a horizontal component and a vertical component. Let's see if I can find that.
yes, we call it bloat, conductor bloat, but this term I did not hear, horizontal sag.
Yeah, so that, give me a second here. Mm, Yeah, hold on. So hopefully now you see aerial cable behavior, effective wind loading.
Yes,
And so when you have wind, the wind blows the cable out. So the cable has sag, but then, I mean, this is the cable in this illustration, but you can characterize the sag as the horizontal component, and it's usually called the horizontal sag, and the vertical component. So that's what I meant when I was talking about how the programs will generate that. And on that particular example, for whatever reason, when I was doing those sag and tension calculations, I separated the horizontal and the vertical sag. But you could then calculate what the total resultant sag really was. Does that answer your question?
yes. So
Okay.
I understand this conductor bloat, which you named as horizontal sag,
Yes.
and the impact of wind and ice. I know it could be because of wind. Once we calculate sag, we use resultant weight because of conductor wind pressure and ice loading. If there is, then sag is calculated. I am familiar with that process, but the term used horizontal sag probably I heard first time. So it's good information. We call it
Okay.
conductor bloat.
Okay. Well, good. Yeah. Yeah.
Thank you for that.
Yeah, the
So I
horizontal
have,
component is really your blowout. Yeah.
yes, horizontal vertical load and horizontal load, and that determines conductor weight and then sag. So it's interesting to know that you mentioned the error in the sag calculations. But once we issue a stringing chart for construction, we provide tension and sag at different temperatures, and in the field, we keep some margin for construction errors, but once we check it after installation, the contractor checking with dynamometer, so the sag almost match with the calculation what we provide. Tension is matching and tension and sag both almost matching, not 100%, but they are
Okay.
matching.
Well,
Yeah.
great. And I really mean that. If it matched, great. So, Other questions? I see a written in chat, ADSS has very little thermal elongation, but stretches a lot more than ACSR in response to ice and wind. How do folks design the ADSS underbuild to stay in the same easement as the distribution? Yeah, that's that's a great question. It's one of these real world things though. You absolutely should be checking the blowout on ADSS to make sure that you're staying within the easement. But how many utilities just kind of forget about that or ignore it? I couldn't say, but I bet there's a lot if I had to bet. I'm just saying. So other than that, I'm not sure what to tell you. If you're concerned about that, yeah, you should check it. And then what you would do is if the cable's blowing out of the easement, then you would need to tell the cable manufacturer that they need to adjust the design so that there's less blowout. How are they going to adjust the design to do that? They're going to have to make the cable stronger. Effectively changing the modulus so that there's less sag under whatever the design condition you have. So yes, you can do it. And I applaud you for being attentive to that because I think a lot of utilities, their distribution departments or their departments dealing with ADSS just ignore that. So other questions?
Mike, could I make another observation, especially
Absolutely.
about field installation of conductors? If a conductor, if the sag of a conductor is being installed using a survey instrument, like a total station or even an old engineer's level, the sag can be, the conductor can be brought to its initial sag, very precisely, well within the diameter of the conductor, because that instrument is very precise. Conversely, the dynamometer installation techniques, part of my comment has to do with the scale on like a mechanical dynamometer. And it's very difficult to interpolate between the markings on the dynamometer. So you're not going to get, 3 or 4 significant places of tension measurement out of looking at a mechanical dynamometer. And and for the digital dynamometers, that's a function of where the dynamometer is. Is it in series with the dead end? Is it in series with a come along that's pulling the conductor up to final tension, or is it down on the puller itself, which is reading the tension that's going up to the first set of blocks instead of the horizontal tension on the span. So there's a number of sources of error. A lot of contractors like to use dynamometers to install conductor, and that's okay for very short spans, pull-offs from substation racks and that kind of thing. But if you've got a 500 or 1,000 foot rolling span line, that dynamometer could be a source of errors, basically, depending on where it is, if it's been calibrated, is it digital or mechanical? So, my preference is always to have the conductor installed with some sort of a survey instrument or sag boards or some of the other installation techniques that actually measure the sag quite precisely, rather than the tension.
Yeah, I agree.
But that's personal experience and preference.
No, I agree with you because what I've seen, my own experience, I think dovetails with yours, that dynamometers often aren't calibrated, and the where they're placed. You may not be reading what you think you're reading. As a practical matter, if you put a dynamometer in series with the dead end, then when you take the dynamometer out, you have to pull the dead end up to the structure. Well, now you've actually changed your sag and tension. So,
Well, yeah, if the dynamometer is in series with the coffin hoist, that's a little bit better because you can pull the conductor up to tension, and then you don't have to compensate for the length of the dynamometer coupling. However, what that dynamometer is reading is not the horizontal tension. It's reading the resultant tension at the structure, which, you know, may be close to horizontal tension. I don't know, maybe close enough. You know, but for a you know, if it's on the uphill side of the structure on the uphill side of a span, a dead end span, it can be way off just because of the angle. So there's a lot of things to consider. You know, it's not only a design issue; it's a construction technique issue as well. For getting the sag and tension correct.
Yes, I would want to say something that we never recommend dynamometer to verify the sag. So most of the time we ask contractor to use sag board and verify or use the wave method. But I have worked on the project in the past where we have a much longer span. I worked on a 380 kV transmission line project overseas. So with average span 1500 feet. So I got a chance to measure the sag using IEEE 524 method using total station, what Joe was mentioning before. And sag was, you know, few inches difference there was after sag. What they were doing, that they were marking using line of sight on the tower and marking the sag on the tower, and then during the final stringing, they were marking where the horizontal, suspension insulator are straight, they mark on the conductor, they clamp it, and at the end, they were dead ending it using the dead end, last span. So in this way, they were controlling, there's no change in the sag.
Well, it sounds like a very good process.
Yeah.
yeah. Mhm. I see a question here. If actual tensions appear higher than what was designed, either conductor was strung too tight or conductor already seemed like it was in creep, would you say if it's within 10% of design that that's acceptable? Wow. I guess I would say that that's acceptable. I guess what I've been saying through this presentation is I think field error of plus or minus 10% is pretty darn good in the real world.
And it's compensated for by typically by buffers, you know, that get added to NASC ground clearances.
Yeah. There's margin for error built into your structure design, and there's margin for error built into the code clearance requirements. So I think you're okay. All right. Any other questions? All right. I appreciate those of you that's stuck around here for the end. You know, thanks for everybody's participation today. Again, look for the follow-up email, and there'll be those 3 links in there. And please do give us some feedback. And I also saw that Alexis posted, we're doing a survey. What topic would you like for us to cover next? So please give us some feedback. Enjoy the rest of your day. And we're coming up on the weekend, so have a great weekend. Here in the States, it's Labor Day weekend. So enjoy the long weekend at that. And we'll see you next month.
Thank you, Mike.
Thank you, Joe. Bye-bye.
Thank you.